All right, number five, or fifth one, I've labeled this as tougher. For grade 11, this is really as hard as I can make it. In grade 12, we'll add another form of energy just to complicate things, but this is really the pinnacle of difficulty for conservation of energy for now. Um, we could talk about efficiency and things, but for now, this is as tough as it's going to get. So if you can handle this one, you're good to go. Um, I haven't been doodling little pictures, but I'm going to doodle a little picture for this one just to emphasize it. We've got the ground. We've got a volleyball. I'm not good at drawing volleyballs, but let's pretend that's our volleyball. I don't know the direction, but it's moving at 12. The cool thing about energy is I don't need to know the direction. And it says it was 2 meters above the ground when this happened. It's going to go flying through the air, crash somewhere, so it kind of feels like a projectile motion question. I'm curious about how fast it's going when it crashes. Notation-wise, when there's an initial and a final in energy, sometimes people write it as V, and V with a little apostrophe, or a V prime they call it, to indicate that the prime is the second speed. So this one's a little bit different. It started off up high, so it's got gravitational, and it was moving, so it's got kinetic as well. It started off with both forms of energy. It ended up at its lowest point, but moving faster. Since it's at its lowest point, it doesn't have any gravitational anymore. It just has more kinetic. So it goes from gravitational and kinetic to having just kinetic. Notation-wise, I'm going to put that little apostrophe on here, the little prime, so I don't get my EKs confused. Sometimes you use an analogy of money. The volleyball started off with money in two bank accounts. It had a little bit of money in its gravitational bank account, and it had some money in its kinetic bank account. It's going to take all of its gravitational money and convert it into the kinetic energy account. All the joules end up as EK prime. And then, knowing our equation, we can figure out how fast it's going for having that many joules of kinetic. We can't simply crank out the mgh and the 1/2 mv squared since we don't know the mass. But when we set up the equation, then it'll fall apart. It started off up high, so it started off with mgh. It started off moving, so it started off with 1/2 mv squared. It ended up moving faster, so it ended up with some 1/2 mv squared. I'm going to use that prime because it's a different speed. In these conservation of energy questions, the m often cancels out, so we can do that again. So now we can do our plug and chug thing. 9.8 started off at a height of 2. 1/2 started off at a speed of 12 equals 1/2 times, I don't know, squared. You can do a bit of plug and chugging. I get that this stuff on the left works out to be 91.6 within some rounding, and that's equal to 1/2, I don't know, squared. Flip the 2 to the other side, then my I don't know squared is, I'm getting 183.2. You may disagree on some decimals depending on rounding. Square root that, and I'm getting 13.5. That works out to be meters per second. That's how fast the volleyball is going when it gets to a height of 0. This is about as hard as it can get. When you start looking at the worksheet, you'll notice there's some questions that kind of go the opposite direction. So here, I'll doodle a new picture. What if I made up a question that said a volleyball, or let's say a soccer ball, is on the ground. Someone kicks it at a speed of 13.5. Someone over here catches it at a height of, I want to match this question, at a height of 2. How fast is it going when they catch it? Although it kind of looks different, this one that I doodled in red is kind of the opposite of the one we just solved about the volleyball problem. If something starts off down low but moving quickly, it starts off with a lot of kinetic energy. When someone catches it up high but still moving, it's still got some kinetic energy because it's still moving, and it's up high, so it's got some gravitational potential energy. So I could flip, you'll see on the worksheet there's some questions where things start off down low and really fast and end up higher, moving slower. For those, we'll just flip our energy around. It starts off with a lot of EK and converts it to EK and EG. Perhaps if I give you the height, like this one I doodled in red, by giving you the 2 meters, you could find out how fast it's going. Or if I wanted to change it, I could say that it's up high in the air and it's moving at 12 meters per second. You could calculate how high it must be. So those are what I called the tougher ones, but there's really only two versions of it, EG and EK being converted into EK, or if we kind of reverse it, EK being converted into EK plus EG. Try those last ones on the worksheet, see how it goes.